Well, good day, everyone, and welcome to our webinar this morning on ventilation in the hatchery. Welcome also to our Spanish-speaking customers. Bienvenido también a todos nuestros clientes que hablan español. La próxima semana tendremos la misma clase. Si desea verlo en próximo martes en lugar de hoy, puede visitar www.chickmaster.com y registrarse allí ahora. My name is Mark Sintel, and I'm the Vice President of Customer Care for Chickmaster, and I just want to welcome everyone. And while we can't see each other in person quite as easily right now, we are really honored that you would choose to join with us virtually to talk about ventilation issues in your hatchery. If you have questions during the presentation today, please use the Q&A button below, and we will interrupt our presenter and ask those throughout the presentation. So feel free to be as interactive as you'd like to be by asking questions using the Q&A button. You could also raise your hand if you'd like to ask your question, and I will unmute your microphone for a moment. Please be aware, though, that we are recording this presentation so that it will be available to others later. So you may prefer to type instead of talking. Our presenter today is Chad Daniels. Chad has been with Chickmaster for 12 years, and before that was 20 years or so with Tyson Foods. He's currently our global director. He's the global director of all of our hatchery specialists worldwide. He's got a great team, and Chad has forgotten more about incubation and ventilation than many of us will ever know. And so we're really in for a treat today as Chad shares with us. So without any further introduction, I give you Chad Daniels.
Good morning, everyone. This is Chad. I hope we're able to do a good job today with discussing some hatchery ventilation tips. I'll begin with talk about the agenda. Understanding embryo requirements for development will be the first area of topic that we'll discuss. Some ventilation basics, managing room conditions, and then results for poor ventilation. To begin with, understanding embryo requirements for development, we understand that the quality of the hatchling will depend largely on how the embryo is able to utilize the nutrients that are provided within the egg. When we look at an embryo during development, we realize that it requires oxygen, and it also releases carbon dioxide and water vapor. And if incubated correctly, is able to utilize these things as nutrients. When we look at the basic requirements for embryonic development, we understand that temperature, humidity, turning, oxygen, and CO2 all play an important role for incubation. And we want to discuss today how ventilation plays a key role in allowing us to manage these processes. To begin with, temperature, we recognize that during embryonic development, the egg in the beginning is endothermic, meaning it requires heat in order to get up to incubation temperature. Next, it transitions into an exothermic, and therefore it is producing more heat than the embryo needs in order to continue development. So when we look at the chart that I've presented on this slide, we see around day 8 to 10 where we start to see a big spike in the red line, which is the temperature production or the heat production from the embryo, or the CO2 is the red line, I'm sorry, the black dotted line is our heat production. You also see as that heat production continues, we see the increase in oxygen consumption, and we see the increase in CO2 production. And these are all associated with the size of the embryo during development. When we look back at our list under temperature, we know that the embryo requires a higher temperature in the beginning and a lower temperature in the end. And therefore, temperature becomes a function that requires control, adding heat in the beginning, removing heat in the end. For humidity, external humidity affects internal moisture. As the embryo develops and becomes exothermic, this causes an increase in moisture loss from the egg. Increased internal moisture loss creates higher levels of external humidity, and therefore creating another function of control through the incubation process. When you look at this on a large scale, we take an example of a large Avita single-stage incubator that holds 126,720 eggs. If the average egg weight is 65 grams, and we have a target weight loss of 11% over the 18 days, the total loss is 7.1 grams, or total moisture loss equals 899 liters or 237 gallons of moisture. It kind of puts things in perspective of how much moisture is actually lost during the incubation process. Obviously, turning is a requirement to keep the yolk from settling through albumin, attaching itself to the shell wall. Also allows full development of the chorioallantois membrane, the vascular system that lines the interior of the egg, improves airflow around the egg. And then we'll just talk about oxygen. So oxygen is a vital nutrient. The embryo requires this nutrient in order to develop correctly. Oxygen consumption begins with the development of the vascular system, which is very early in the incubation process. Consumption increases proportionally as the embryo development advances. And then as the embryo consumes oxygen, it produces CO2, which brings us to CO2. We know that this production is proportional as the embryo develops. And we also know that CO2 exposure at specific times and specific levels enhances embryonic development, and therefore it becomes a function of control. So when we talk about these requirements, we recognize that in modern incubation today, whether it be single stage or multi-stage, we have the capability of the machine to control the temperature, humidity, turning, and CO2. What about oxygen? Oxygen is provided to the machine via the ventilation system supplying the room. So now let's talk a little bit about ventilation basics. When we begin, we know that we have a developing embryo that is in an incubator. This incubator is in an incubator room. The room is in a hatchery building. And then external to the building, we have ever-changing atmospheric conditions, which include changing temperatures and changing humidity conditions. So the ventilation system within itself, by design, still has to provide the incubator, the embryo, that needs to develop correctly and deal with the atmospheric conditions. So when we look at some of the earlier basis for around ventilation design, we recognize that evaporative cooling units, which were nothing more than a fixed blower that provided 100% fresh air into a room. Essentially, the air was cooled by drawing the air across a water-cooled or a water-soaked cardboard, generally, or a filter pad. And as that air drew through that pad, moisture would evaporate and therefore absorb heat and create a cooling effect. As things advanced, we saw rooftop HVAC units be developed that have multiple stages of heating, multiple stages of cooling, oftentimes hot gas bypass reheat for dehumidification functionality, modulating outside air dampers to provide a mixture of fresh air into the room. And all of these things being designed into units require advancements in control systems. And therefore it becomes a complex issue in most hatcheries. So when we take it a step farther past the controls, we get into having to understand the basics of managing our room conditions. So when we look at these conditions, the most critical by far are obviously controlling the temperature, controlling humidity, and controlling pressure. And let's start with what is generally the toughest to comprehend in most cases, which is the pressure. So what is pressure? Pressure, unlike temperature or humidity, is actually the differential between two reference points. So when we measure and control pressure differential, it guarantees a correct amount of fresh air in the room, supplied to the incubation equipment, exhausted into the plenum, and then to the atmosphere. So when we look at our illustration, we recognize the blue arrows are the fresh supplied air coming into the corridor. That air then is consumed by the incubation equipment and then exhausted into the plenum, where variable speed fans then exhaust this used air to the atmosphere. So when we talk about measuring the 2 points or 2 reference points, we recognize that we want our room to be positive, and we have our atmospheric, and in order to control our room positive, we reference to the atmosphere, and therefore that's our 2 reference points for being able to control the room to a positive pressure. When we talk about managing plenums, exhaust plenums, we have a negative pressure by desire, and therefore we have a negative plenum that references back to the room. And that's the normal recommended way of referencing these points. So when we control pressure in a hatchery, we try to control the room pressure to a slightly positive or a positive setting specific to your needs, and then we control the plenum. But then the atmosphere becomes our other point of reference. So in order to control these 2 pressure settings, we have to have the adequate and correct pressure referencing of 2 points in order to control it. So when we talk about a classic multi-stage setter, we recognize that the overhead fans internal to the machine create static, which allows the machine to self-ventilate. And what do I mean by this? When we reference to the figure, we recognize that figure 1 is a positive setter room. Figure 2 is the fresh air intake duct internal to the machine. And reference 3 or point 3 is the positive side of the fan. And if we look at this, when these fans are operating, we recognize that there's as much as a 0.12 inches of water column static between the negative to the supply in these internal fans, with the internal fans operating. And that pressure alone, creating that negative pressure in that fresh air intake duct, is what allows this machine to consume air from the room and therefore exhaust it out of 0.4 port to the exhaust plenum, and therefore our plenum, being number 5, then only has to run at a slightly negative pressure. So when you have a machine such as this classic that creates its own static pressure, very little differential pressure is required across the machine in order to control airflow. When we take this a step farther and we look at an Avita single stage incubator, we recognize that the internal paddle fans manage air circulation through the egg pack, but they do not create a high static. So when we look back at our figure, we recognize there's very little pressure at all between 0.2 and 3, simply because of the positioning of the fans and the job that the fan is designed to do. So therefore, it does require a pressure differential to control airflow through the machine. And what you'll recognize with the Avita is that there's a big difference in pressure 0.2, which is that reference from the exhaust plenum back to the room. Again, this is by design to allow the fans to not waste energy in moving airflow through the machine, but to do a better job of internally recirculating air through the egg pack. So the keys to success when we talk about controlling room pressure is to maintain a positive room pressure, whether it be a setter room or a hatcher room. You've got to control a positive room pressure at all times. Exhaust plenums for classic multi-stage should only be slightly negative. And in bold, do not over-influence the machines. When we look at the exhaust plenums for a VITA single stage should be adjusted to meet the CFM requirements of the embryo. And this is going to range between 2.8 to 3.2 CFM per 1,000 eggs. This should be measured at the exhaust with a full machine in a turned position with the damper at 100% or full open. And I'll show you an illustration of using a handheld anemometer to measure feet per minute. Is in this illustration 517 feet per minute is measuring airflow being exhausted out of this machine. So when we look at recommended static pressure settings for the various incubation rooms, setter rooms, generally whether it be a classic or single stage, we generally recommend a slightly positive pressure of a 0.02 inches water column or 5 pascals. For setter exhaust plenums on a classic, again, to not create too much differential pressure, we have a recommended setting of a negative 0.02 or a negative 5 pascals. And that is in reference back to the room. When we look at an VITA or a single stage incubation, we have a much bigger range of recommendation. And that range could be anywhere from a negative 0.04 to a negative 0.12. And that's negative 10 to negative 30 Pascal. The reason for this variation in recommended settings is all associated around the various size availability of the VITA. We have machines that are as small as just a 1 or a 2 trolley machine, and then getting into standard sizes is a 6 trolley or a 1 zone machine, a 2 zone or a 12 trolley, and then you have an 18 trolley, and then the 4 zone 24 trolley machine. So the bigger the machine is, the greater the differential pressure is required in order to get adequate airflow through the machine. And that's due to the size of the machine and the egg capacity. When we look at hatcher rooms, generally hatcher room, again, we want to maintain a positive, but we want that positive reference to the atmosphere to be slightly less than the positive pressure of a setter room. And that's in order to maintain biosecurity. We don't want air from the hatcher room bleeding back into a setter room. So the hatcher room reference generally is a 0.015 positive or 3.8 Pascal in reference to the atmosphere. For hatcher plenums on a classic hatcher machine, we're talking a CBH 90, 96. Those machines, again, are similar to the incubator, the classic, where the fan creates a static, and therefore it doesn't require a very negative plenum. So generally with classic, we recommend a starting point of a negative 0.02 or 5 Pascal, negative 5 Pascal. When we talk about the C192, C384s, those hatcher machines have the internal paddle fan, which is again not designed to create a static, and therefore there is a more negative range required in order to control airflow through the hatcher. And that range could be anywhere from a negative 0.06 to a negative 0.18 or negative 15 to negative 40 Pascals. And that again is in reference to the room. And oftentimes when we look at hatcher machines, we forget that it's critical to use an anemometer to measure air being exhausted out of the machines to verify that you have adequate airflow for the machine.
Hey, Chad, I've got a question that came in. If you go back to that previous slide, or two questions. First, yeah, if you can,
Where's my
there you go. Previous, there you go. First, these reference numbers here, where would someone find them? Are these in manuals, or should they call our help desk, or copy them down here? Where would you find this information in the future?
Historically, the pressure referencing and airflow requirements are generally provided on the specification sheets for the incubation equipment.
Okay.
If you're in an older facility and you did not have or do not have on file what the original specification sheets were, you can make a reference back to Chickmaster, request from Chickmaster, a specification sheet or documents to support the ventilation requirements or settings for your specific machine.
Okay. And so they can always email support@chickmaster.com with specific questions, and we'll connect them with you or another hatchery specialist on that. The second question came in from Tolga saying, hi, Chad, people tend to set pressures to max, and I think there are some problems such as uneven EST when set to max. How do you think we need to decide what we need between -10 to -30 pascals?
So in reference to that, Tobin, that's a great question, and thanks for that. And the EST that he was referencing to as an acronym is eggshell surface temperature reading. And the thing that we recognize is airflow through the machine. The goal of that airflow initially is to provide adequate oxygen to the embryo for proper development, because it's utilized so heavily as a nutrient and as a requirement. Anything above or below the minimum requirements, you get into a situation where you can be air cooling a machine too much if you set it too negative, or if you don't set it negative enough, you adversely affect the ability to provide adequate oxygen to the embryo. And so that's why I always try to focus on making recommended measurements on the machine and knowing what your actual CFM of air through the machine is in order to make sure that you're not outside of that range. Because yes, if you get too negative on a small machine and you have too much airflow, then the machine has to respond to that. That air from the room will generally overcool the machine. It may overdry the machine, and therefore now the machine is too low in humidity, and it may be having to heat at periods of time to overcome the increased air volume. So the key to it is measuring airflow.
Okay, thanks. Another question came in from Irfan. He asks, what is the effect on DOC if we set the room pressure too high?
So if we set the room pressure too high, what has a tendency to happen is it makes it a little bit tougher to maintain, because a high room pressure generally forces doors or traffic doors into the room. It generally forces those doors to leak more air to escape from the room without being properly utilized for incubation. And therefore, energy consumption gets considerably higher. When this air comes from the room, it has to go somewhere. It's going to leak into a corridor. It's going to feed other areas of the hatchery, and then you have to deal with it in other areas. So while the room is critical, that the room is slightly positive, telling us that we are feeding the room with enough air to feed the incubation equipment, we don't want to get it too positive, because the byproduct of that then is just overuse of energy and too much pressure on the doors.
Okay. Another quick question. What are the recommended CFMs for a classic hatcher?
So on a classic hatcher, it is a machine that doesn't necessarily do a great job on the older classic hatchers. It doesn't necessarily do a great job of cooling itself strictly with the water cooling that's internal to the machine. So it relies heavily on airflow to provide some of that cooling source. And so the key with that particular hatcher is to be capable of providing in a range of 10 to 15 CFM per 1,000 egg set capacity. So commonly with the older hatcher machines, it's very common to have a plenum set at a negative O2 in reference to the room, say at transfer. This is when the embryo is still internal to the shell. It is not externally pipped yet. And the heat production at that particular time is a little bit easier to manage. But then as you progress through hatch, the chicks pip, they get into a dry down mode. Now you have down that you have to deal with collecting on the cooling coils. At that point, it's very common to take a plenum slightly more negative and aid the machine with additional airflow, and therefore you get closer to that 12 to 15 CFM per 1,000 egg in order to manage vent temps leading up to pool.
So this is kind of related to that last comment you made. Robert says, we have trouble with fluff buildup clogging the cooling coils on the hatchers. Is this a water temperature or pressure issue, or a static pressure issue, or both?
Yeah, it can be a combination of multiple things. One being the pipping process produces a lot of moisture in the hatcher machine. And with that moisture at that specific temperature, generally in the neighborhood of 97.8, 97.9 at time of pipping, you can reach condensation dew point on your coils very quickly. So managing chilled water temp in your hatcher is important. You don't want that water to be much colder than, say, 58 to 60 degrees in a classic, or you'll have an exceptional amount of chick down. And the other piece of it is servicing the machine with adequate airflow in order to keep the machine from calling for too much chilled water demand.
Okay. All right, I've got two more, and we move on. These are great questions, everyone. Thank you for sending them in. This is kind of a practicality of how do we take temperatures. Liam is asking, says, we have aux fans on our hatcheries. We have aux fans on our hatchers. When I take my CFM measures, am I supposed to do that with aux fans on or off?
So for a hatcher machine with an auxiliary fan, the first measurement you take is with the fan off. And with the fan off, you want to set your plenum pressure in order to achieve in that range of about a 7 CFM per 1,000. And then with the aux fan on, that's where you want to be capable of achieving up to, the 10 up to the 15 CFM per 1,000 range. So you want to take that as a two-step process. Measuring it without the blower verifies that you're capable of moving adequate air for oxygen demand and to deplete CO2 without the blower. But then when the blower comes on, you just want to make sure that you're not overwhelming the machine with too much air, but then you want to make sure that your auxiliary fan is being effective.
Okay. All right, and maybe just one more, for those that are maybe a little less familiar, could you just kind of one more time explain the classic static pressure that inherently lets the incubation suck the fresh air and exhaust the air, please? So maybe just a quick review of this before you move on into the effects on the embryo for ventilation.
Yeah, so let me go back quickly to this slide. So when we look at a classic machine, this is the illustration here shows a side view of the classic incubator. And you have the 6 overhead fans on our C540 or C576 machine. What you recognize is the fresh air duct, which allows air from the room to enter the machine. This duct internally has openings above each fan. And therefore that opening is strategically located in an extremely negative suction of that fan. And therefore, when the fan is running, that extreme negative just above the fan is what allows that air to be pulled in from that fresh air duct. So we recognize with a classic incubator, and I talk about it as a self-ventilating machine, because we recognize this machine could just be constructed in an open environment with no room pressure or no plenum pressure, just strictly a machine standalone. And by turning on the fans, that machine will draw air into the fresh air intake and will exhaust it out the exhaust ports due to that pressure differential created by the fans.
Okay, I think we're good to move on at this point. Thank you.
Okay.
I have another specific question, and I'll just mention this here. Some specific questions are coming in about specific room conditions and specific ventilation systems, folks that have CC3s and recommended pressures and things like that. And we're not ignoring your questions, but we will have someone call you back to talk about your specific site. But if we start to get 2 or 3 questions on the same thing, we'll ask them publicly. But thanks for your questions. Keep sending them in.
So when we talk about managing room conditions in the name of pressure, we recognize pressure plays a big role in biosecurity. And so when we look at this illustration, we recognize that by design, the blue highlighted area is what we reference to as we try to maintain as a clean side or clean area. When we look at more into hatcher rooms, takeoff rooms, chick rooms, chick processing, these are dirtier areas of the hatchery. And so when we look at a pressure cascade, in other words, pressure settings for egg rooms, setter rooms, transfer, as we progress through a hatchery, you want to try to make sure that your pressure settings aid in allowing air from cleaner areas to progress more towards dirtier areas. And that allows some support when it comes to trying to control biosecurity. So in other words, we don't want the dirty air from a hatcher room to essentially be allowed to migrate back into a setter room. So when we look at pressure settings or recommended settings per room outside of incubation areas, generally we look at an egg room that we try to maintain at a 0.03 or slightly more positive than the setter room that it's connected to. Transfer room, we want it to be neutral between a setter room and a hatcher room. So we definitely, during transfer, we don't want air from a transfer room to migrate back into a setter room. And same with takeoff. You'll recognize that the takeoff, or commonly referred to as a pool room, is generally the most negative room in the hatchery. And I want to point out that while we recommend it to be negative 0.02 or a negative 5 Pascal, a lot of times you go into hatcheries and you'll find that this room may be a negative 0.1 or a negative 30 Pascal. And if you keep it too negative, essentially it can pull a lot of fresh air from the entire hatchery, and it can negatively influence your ability to maintain positive pressures in any rooms that are connected to this. So we try to keep a chick room neutral, washrooms slightly negative, clean rooms slightly positive, the 0.02 to 5 Pascal. I'll show you another illustration where we recognize that even in dirty areas, there are places that we want to have more positive than rooms next to it. So when we talk about biosecurity, we always want to try to supply our fresh outside air to the clean rooms and exhaust from the washrooms. As a perfect example with the chick box return and wash, and then your clean box room. So the dirty boxes returned from the farm, they're stored in a specific area and then washed, and as they come out of the washer, they're stored in a clean room. In this application, you would provide all of your fresh supply outside air into your clean box room and allow that to migrate through and be exhausted out of your chick box return and wash room. So therefore, the clean box room does not have an exhaust fan. Essentially, all the fresh air And the ventilation is designed in both of those rooms in combination. Supply in the clean room, exhaust out of the dirty room. And that keeps anything that's dirty in your dirty area from migrating into your clean area. Same holds true for rack washrooms or hatcher basket washrooms off of your takeoff room.
Chad Tolg is asking again, before you move on there, if you supply positive pressure at the egg room, you'll ventilate your storage. Do you think that's energy efficient? Also, I will lose room humidity and need to add it. Do you think there's a risk of contamination?
So when we look at an egg storeroom and trying to maintain a slightly positive environment, if you don't exhaust out of that area, or if you do exhaust out of that area, in order to maintain a slightly positive, it really takes a very minimal amount of fresh air to keep that room positive. So if I have an egg storeroom that's completely isolated, let's say by corridors that separate it from the setter room or from other areas, then it's not near as critical to try to keep that room positive as opposed to if it's directly, such in this illustration, where it's directly connected to the setter room and say egg handling. And so therefore, if that egg room is neutral, in this application, anytime someone opened a setter room door, air from the setter room is going to bleed into the egg store. And we really want to try to avoid that if possible. And you either do it with a corridor separation, or you try to maintain that egg store slightly positive. And it may only take a couple of hundred CFM to keep that egg store positive, because you're not really exhausting a lot of air out of there. In other words, normally in an egg store, you don't have any exhaust at all. So it takes very little supply air to do that.
Okay, and then the second half of that question was about contamination of needing to reintroduce some humidity if it's lost.
Yeah, so due to the temperature that you're controlling most egg stores at, it completely depends on the atmosphere. If you're in a very dry, humid, or a very dry climate where there's very little atmospheric humidity available, again, due to the lack of air exchange in an egg store, it does require some humidity, but not a tremendous amount, because we're not setting up an exchange of thousands of CFM. We're talking a few hundred CFM. But in an environment oftentimes where it's extremely humid as an atmosphere around, generally we see egg store in that particular application where very little or no humidity is ever required, just simply because the atmosphere provides it.
Okay. Is it important to supply air to the egg room and set the right pressure inside that particular room, given that the egg room has its own air cooling unit in this particular person's facility?
And again, yes, it is important to provide some fresh air to that room because again, that lets you maintain a positive. Now, is it critical that that is a controlled positive? In other words, do we have a modulating damper on a fresh air with a supply pressure referencing to control that damper? It's not critical that that be accomplished as long as you have a mechanical capability of setting it. So if you have a supply fan, what's very common is just a very small supply fan bringing fresh air directly into that room from the atmosphere. Generally, you want to make sure that's filtered. And you want to make sure that it's brought in at a point where it mixes well with the room. So with, say, rooftop HVAC units, it's pretty easy to set a manual outside air damper at a minimum of, say, a 5 or a 10% opening to allow that fresh air to be drawn in through that unit, and therefore it mixes with the air being supplied to the room.
Great, thank you. And one last before you move forward, is it important to supply, I think we got it. How about, I think there's unbalanced condition between air supply and air exhausted. I'm not sure the nature of the question there. Why don't we move on, and if you'd like to rephrase your question, perhaps we'll understand that in a second.
Okay. So when we talk about managing room conditions past pressure, we get into talking about temperature and humidity. What we're illustrating here is a maestro graph from a classic incubator. And what we recognize with a classic or a multi-stage incubator is generally that machine runs with a fixed set point, and therefore it's consistently at the same set point all the time. We do recognize that there are times where the temperature will have a dip, and in this reference you see that more than likely it was an egg set that occurred in the machine, and therefore the temperature dropped. A lot of heating ensued and brought the temperature back up to a stable temperature. But keeping a consistent room temperature and humidity is critical with the classic, just simply because the machine is trying to maintain the exact same temperature all the time. We also recognize that air volume through the machine essentially is very consistent, and we see that a damper physically runs more in an open position by design due to the nature of how the machine operates. But with the consistently open damper, consistent CFM, and consistency in temperature and humidity set points, it becomes critical that we control temperature and humidity as consistent as possible in the room. When we look at a single stage machine, or an Avita in this particular case, we recognize that the machine starts at a higher temperature and then the temperature stages down as embryonic development continues. And we see that with a continually downward trend. And so when we talk about managing room conditions and consistency with single stage, we focus on the fact that the CFM is minimal or zero in the beginning, and it continually increases. We see that the damper opening, the blue line, starts at a relatively low point and then slowly builds open as the embryo continues to develop and therefore requiring more oxygen. So the most critical thing when it comes to managing the room conditions in a single stage focuses more around the last 5 to 6 days prior to transfer out of that incubator. Because at this point, the machine is running a very big damper opening. It's at its coolest temperature settings and is requiring the largest demand of oxygen or CFM ventilation from the room. So this becomes our critical control point. When I look at temperature recommendations, we recognize that there are some varying differences between, say, a multi-stage room versus a single stage room. So egg rooms, generally we see ranges between 62 to 68, 60 to 65% relative. Multi-stage rooms, 77, 78, 50 to 55% relative. And then look at single stage setters, slightly lower temperature and quite a bit lower relative humidity setting. Hatcher rooms, 75, 77. Chick rooms, 75, 77, transfer, pull wash rooms. So there's not a huge range of temperature requirement when it comes to providing pretty much all of the incubation rooms and the processing areas, with the one major difference simply being the egg room itself when it comes to temperature control. When we look at objectively trying to provide a consistent environment into the room, I'm showing an illustration of a typical supply air distribution using either a central system, an ARIA, or a CC3 system. Generally by design, we have an overhead duct that is in a plenum or an attic area, and that duct then allows distribution of the air full length of the room. So you have an even distribution. Because we're controlling the supply air being fed to the hatchery, we'll see a supply range of 76 to 78 on a system similar to this, and therefore you're going to have a very consistent room temperature. And with consistency in temperature, it makes it easier to be consistent with humidity as well. When we look at a typical HVAC system, you recognize that your distribution points in the room are pretty minimal. Your supply air is essentially one duct that discharges air two different directions in the room, and you only have one return point. And with this, we can see a variation in air being supplied to machines. So machines that are very close to the return duct will see a more consistent temperature versus machines that are closer to the supply air discharge, and they'll see that big variation. So when we talk about rooftop HVAC units that have stages of cooling due to compressors, number of compressors, and we see gas-fired heating or heat exchangers that cycle, we see a large discharge air temp variation. Been measured as low as, I've measured them even lower than 60, but under normal circumstances, we'll see it vary from 60 to 120 degrees, and therefore create a pretty inconsistency in the air being provided to the machine itself. So it's important with a system like this to do everything possible to adjust your discharge air grills so the air is being mixed in the room as much as possible before being introduced to the machine. It's also important to try to make sure that none of the discharge grills are pointed directly at the air intake of either the incubators or the hatchers. So let's talk about some results from poor ventilation. So when we look at some of the things that are a byproduct of poor ventilation, we see unstable temperatures, oftentimes too high and too low, unstable humidity, too high and too low, and then we also see unstable pressure control, which leads to reduced airflow or reduced oxygen. So we look at unstable temperature. If our temperatures are too low, we often see increases in heating demand for the machine. So if a machine is a multi-stage machine or single stage with a bigger damper opening, and we have a room that is extremely cold, in other words, much way below our recommended setting, you will see the increased heating demand for the machine. We recognize anytime internally a machine is having to work excessively to make up for the room environment, it's going to create an inconsistency in the microenvironment inside of the machine. And so anytime a machine is excessively having to heat, we're going to see variation in temperatures in the machine. And any variation in temperature is going to lead to reduced hatch and reduced chick quality. So we also recognize if a room is too low, if the damper is controlled by temperature, such as with a lot of the older classic machines, we'll see dampers that'll remain at minimum or will stay. Once you make an egg set, the damper won't open very soon because the air entering the machine is just too cold. If it's too hot, obviously the opposite occurs. We see big increases in demand for water cooling. We also see that if the damper is controlled by temperature, it'll open full range much sooner. And both of these things will cause inconsistencies in the internal temperature control, which is going to affect hatch and chick quality due to incubation time and chick readiness. It's very common with temperatures that are too high or too low, where we see chicks in certain places of the machine that come off way too soon, while eggs being incubated in places that are too cool, these chicks will pip or come off much later. So it creates a big spread in your hatch window and in chick readiness. So in every chick placement, you have chicks that are possibly have been out for too long. They're slightly dehydrated, possibly even overheated at times. And in that same placement, you have chicks that are green or reference to a little bit further behind, maybe unhealed navels, making them more susceptible to picking up bacteria, and not really a chick that is ready to be placed yet. And therefore, you have higher farm mortality as well. When we look at unstable humidity, too high and too low, if the damper is controlled by humidity, obviously it will remain at minimum. which is going to reduce your oxygen and going to produce higher CO2 readings. The setter will use excessive humidification, causing cool spots. If it's a single stage incubator and it doesn't have humidification internally in the machine, then we're just generally going to see lower than normal humidity settings in the machine, and we will see an excess of moisture loss. So we'll have a higher moisture loss from a machine with the too low humidity. If it's too high, the damper is just going to be, wide open, more of a full range. Obviously, chick quality, hatchability affected by moisture loss, because the opposite occurs with too high of humidity. We have a lack of an ability to have adequate moisture loss, and therefore chick quality is greatly affected, especially in the older flocks that's harder to control moisture. When we look at unstable pressure control that we talked extensively about before, if we can't control the pressure or the differential or supply pressure, we obviously see the first thing that adversely affects hatch, which is no oxygen for incubation. That yields high CO2 readings, also reduce heat removal, moisture removal, and then last is the no biosecurity. So pressure control is very critical to make up for all of these factors, which is going to affect machine operation. When we look at some results with no oxygen, one of the first things you'll see is a high incidence of what's referenced to, or what you'll see is urates. So urates is a byproduct of an embryo developing with a low oxygen level. What we recognize is that for that embryo, if it doesn't have oxygen as a nutrient, it's going to utilize another nutrient, which generally, first thing it does is it starts burning proteins. And the consumption of the proteins is going to reduce muscle mass. And the first thing you'll start to see with reduced oxygen is these higher incidence of large volumes of the urates that you see in these pictures here. It leads to late stage mortality. It also leads to poor chick quality, and it definitely affects hatchability, chick quality, and field performance as well with no oxygen. Without the airflow aiding heat removal, you see a variation of things. And this picture illustrates, when we look at the residue sampling on the left side of the screen, you'll recognize a lot of very rough edges on the eggshell when the chick was pipping because of too much heat. You see navel issues such as strings or tags or unhealed navels. Red hocks are also a good sign that you're having too much heat. Chicks that are down in the basket due to an exposed viscera are very common when you have no heat removal. The lack of heat removal creating inconsistencies in the internal temperature can cause chicks to come out early, and you start seeing more scaling on the legs, more vein exposure due to dehydration. And then you obviously see chicks that are still very late coming out, oftentimes because they were overheated and get malpositioned and they don't pip correctly as a byproduct. Also, without pressure control, we don't have control of our biosecurity. So we start seeing air returning from dirty to clean areas, from transfer room to setter room, hatcher room to setter room, leads to high mortality at the farm during the first week, and leads to contamination between flocks. So a well-designed and correctly operated ventilation system will provide correct and stable room conditions, temperature, humidity, pressure, and that's your goal with any ventilation system. And then you want to make sure that it will support the incubation equipment and producing the healthy, high-quality chicks. And that comes from providing an environment that allows the machine to operate consistently without being stressed. In other words, having to heat extensively or cool extensively. anytime the machine is having to overwork, it means you probably have signs of lack of ventilation control.
All right, Chad, just a couple questions keep coming in, and everybody, thank you for your questions. If you do have questions, we have just a few moments left. You can type those in the Q&A button at the bottom. And if we don't get to your question during this hour, we will have someone call you back right away to personally answer your question and talk about your situation. So Chad, how would you compensate for loss of pressure in front of the hatchers due to open room doors and cleaning of the hatchers in process? It's a common issue here in the United States. Eddie's asking that.
Yeah, so it is pretty common to see that, and the first comment I want to make in reference to that is when it comes to controlling airflow through a hatcher, because that becomes the most critical point, is the exact reason why we try to make sure people use a hatcher plenum pressure control reference back to the room. So even though a room is not positive at that time, we're still able to maintain adequate airflow through the hatcher to support heat removal, to support getting rid of the moisture produced by the chicks, aid in killing bacteria due to increased oxygen in the machine, but to support the oxygen requirement of the embryo. As long as that plenum is referenced back to the room and you're still able to control the differential pressure across the hatcher, then the fact that the hatcher room itself is not positive any longer, you're still able to manage most of the requirements for the chick. Doesn't mean that some dirty air from pool or takeoff is going to bleed back into that hatcher room. Potentially, yes. You know, so it's very common to see a process or a pool on the day of processing where people prop doors open out of a hatcher room. And if you have an excessively negative pool room, then there's no way that hatcher room is going to be able to maintain positive, because that pool room will pull all of that air out of there. And you can't control positive if you don't have the doors closed. So it's pretty common to try to make sure people close that door back as much as possible, or put in automated roll-up doors that will close immediately once they exit the room, and try to help maintain a positive. Because if you can't reach positive pressure in the room, it means that generally with an HVAC system or any ventilation system, eventually the damper outside fresh air support to that room is going to reach 100%. And therefore you're trying to bring in a large volume of outside air. And if you're dealing with extreme conditions such as high heat and high humidity of the summer, or extremely cold during the winter, either one of those conditions puts a tremendous amount of stress on your ventilation system. And so anytime you can try to keep that ventilation system supporting that room from having to run at 100% outside air will allow you to control the conditions much better. So focus on trying to install the right types of doors, keep your pool room from being too negative, but the most critical is get that plenum, make sure it references back to the room so you at least maintain the differential across the hatcher machine.
Wonderful. So Chad, we have a variety of questions that are coming in from people about sizing systems. Looks like doing some design work and things like that. And I think I'm going to save those questions that we can take those offline, because they apply to specific conditions. So to all of our guests, Chad does lead a team of hatchery specialists, and we have engineers around the world that are able to talk through your particular situation. So we'd love to do that. And if you ever need help from Chickmaster, you can always email us at support@chickmaster.com, and we will have the right person get back to you right away to talk about your situation. So for those questions that have come in about specific sizing and specific sites and specific areas of the world, we will be getting back to you, and others we invite your questions to support@chipmaster.com. We have more of these webinars scheduled over the next couple of months, and so you can visit www.chickmaster.com to see the complete schedule. These have been so well attended, hundreds of people coming in and watching these. We will be posting the recording and the PowerPoint after this, along with written answers to these questions that have come in. So you should receive a follow-up from us as well as this for some reference material. And so I wanted to thank everyone for attending. And Chad, thank you so much for spending time with us today. I believe one of your hatchery specialists, Carolina Diaz, she is going to be doing a similar presentation next week in Spanish. So if you'd like to jump in again and you speak Spanish, you can maybe get some more of your questions answered next week. So again, with that, thank you, everyone. And we look forward to serving you in the weeks to come. Take care.